Good evening, everyone. Welcome to session number 8 of the Amateur Radio Technician class. I do apologize for the slightly late start. We seem to have had an issue with the link that was sent via email. So I just had to resend the link. Seems as though Gmail might have obfuscated the link itself. So I think that has been rectified. Also, welcome to our new participants in the class. Glad to have you. So let's go straight in. So this is where we are in respect of our curriculum. We are under the section antennas and feed lines. Last class, we looked at antenna polarization, horizontal, vertical, and elliptical. We looked at the different forms of propagation, sporadic E, auroral reflection, meteor scatter, tropospheric scatter, and tropospheric ducting. We looked at the effects of precipitation. We talked a bit more about what the ionosphere was, the sunspot cycle. We looked at the different propagation as it relates to day and night. We talked about fading. We discussed antenna length. We talked about what a beam antenna was, and we stopped on page 34 last class. So just a question in respect of the how a signal or radio waves leave an antenna and propagate. So firstly, let's look a bit about what a radio wave is. So we have a radio wave on the screen, and you can see that the lower the frequency, the longer the wavelength, and the higher the frequency, the shorter the wavelength. So the wavelength is this distance here. If you want, you can use the crest of the waveform. We could have easily used another part of the wave, but from one similar point to another similar point on the wave is one wavelength. But notice that for a low frequency, the wavelength is longer. And let's say for a higher frequency, which is the wave below us here, notice that the wavelength is shorter. So that's the relationship we've been talking about all along. Also, if this is our antenna, when we transmit into the antenna, the radio waves or the radio signal leaves the antenna in whatever direction, depending on the design of the antenna. So this here is meant to represent the radio waves leaving the antenna. So we talked about the concept of radiation angle last class, and this was the basis of a question that we got from one of our participants. So this diagram, I added in an antenna onto the diagram so we can make it clear that this is the antenna here. Notice the antenna is also vertical, right? Vertically polarized. And this is the Earth, or the Earth's surface below here. So when we transmit from this antenna, radio waves would leave the antenna and go, we have the ground wave, we have the sky wave, and so on, right? But our discussion on radiation angle has to do with the dimensions of the antenna that we use. And we said if we are using a quarter wavelength antenna, it has a high radiation angle. So notice this blue line is the radiation angle if we're using a quarter wavelength antenna. But notice that when we have a high radiation angle, the signal doesn't travel too far. It goes to at this point here. Notice this distance here. The signal will travel this far. But if we use a half wavelength antenna, the radiation angle is lower. That's the green line here. So notice that the lower radiation angle will cause the signal to travel even further because of the lower radiation angle. And lastly, our 5/8 wave antenna is the red line. Notice a very low radiation angle. And commensurately, we notice that the signal travels even faster or further, sorry. So the quarter wavelength antenna gets us this far. The half wavelength antenna gets us even further, and yet further still, the 5/8 wave antenna, which is a longer antenna, right? But notice I put the arrows in this direction as well, just to illustrate that. Okay, noted, Charlene. Glad you got through. Yes, sorry about the issue with the link. So glad that you joined us. So continuing, notice that whether it's the quarter wave, half wave, or 5/8 wave, we are showing here that the signal goes off in all of these directions. If it's an antenna type that will allow the signal to go in all directions or omnidirectional, we will see the radiation pattern in a subsequent slide. Let us also look at where our broadcast, radio FM broadcast spectrum is in respect of the amateur radio frequency allocations. We talked about it the last class, however, just added into the slide where the radio broadcast band is, or the FM radio broadcast band. So if I'm listening to 95.1 FM, that frequency is snapped up between these two amateur radio allocations. So these are the amateur frequencies when you get your license that you're permitted to use in frequency terms. Notice 1.8 megahertz to 2 megahertz and so on, all the way. And we also have them listed in wavelengths so that you can see when we talk about the 20-meter band, what the 20-meter band is. If we're talking about the 10-meter band, where the 10-meter band is and so on. But notice that the FM broadcast band is between the 6-meter and the 2-meter band. 6-meter band, which is 50 megahertz to 54 megahertz. And the 2-meter band is 144 to 148 megahertz. Those are the frequencies. But similarly, your FM broadcast band is 88 to 108 megahertz. That's the frequency. And we should all be familiar when we tune our dial, whether it's in our car or home, and we tune that dial to 95.1, that's 95.1 megahertz, all right? So just notice where that broadcast band is relative to the other amateur radio allocations. So we looked at this diagram or similar one last time, and we pointed out the various notations, but we highlighted also HF, VHF, and UHF, because these are the bands that we are mainly interested in the technician level course. But it's good for references. We like to give something extra in our class. So we have all of the other bands here listed for you so you can compare. But what I also put up here is to show that for each of these bands, whether it's HF, and remember HF we said was between 3 and 30 megahertz. VHF was between 30 and 300 megahertz. UHF was between 300 megahertz and 3000 megahertz or 3 gigahertz. But we also listed here the wavelength. So notice the wavelength for HF is between 100 meters to 10 meters, right? So if you had an antenna for the HF band, notice how long those antennas would be. But let's look at the VHF band. And we notice that the antenna or the wavelength is from 10 meters to 1 meter, which is even shorter. So consider wavelength. Think about it this way, that wavelength is the length of the antenna for the particular band. You can conceptualize it that way. So the lower the frequency, notice how long the antenna is. So if you have something operating in extremely low frequency, look how long this antenna is. Imagine that 100 and something kilometers. Can you imagine an antenna that long? Or even, let's say, medium frequency, right? 300 kilohertz to 3 megahertz, 1 kilometer to 100 meters. So those are very long antennas. But when we go up in band UHF, notice that the length, the wavelength is 1 meter to 10 centimeters. So very short. So this is also illustrating to us here that as we go higher in frequency, the wavelength gets shorter, and so too does the antenna or the antenna that we look at for those bands. This is just another diagram to give you a bit of perspective in terms of the radio frequency spectrum. All right, you could look at this on your own time and see what service occupies different parts of the spectrum, right? See, light is inside of here as well, right? X-rays and so on. So this is just for your reference. This diagram here, we have been showing tables of the allocation for amateur radio operators in terms of the frequencies that we are allocated as hams. This is just a little chart to show where in the spectrum amateurs have allocations. So it's a very useful chart to show you, you know, all of these things in what's it, turquoise or light green. This color here, it shows you portions of the spectrum where as a licensed ham or licensed amateur, you're able to transmit in these portions of the bands, right? So this is just another good reference for you. And you notice that amateurs or hams have allocations throughout the entire spectrum, right? Okay, so last class we looked at polarization. There was a slight error I had on the slide, corrected it for this slide. So we can quickly look over polarization. Remember, we talked about vertically polarized antennas, and we said that that's when the electric field is perpendicular to the Earth's surface or 90 degrees. We talked about horizontally polarized antennas, and that's when the electric field is parallel to the Earth's surface. And we also said that when we are using antennas and radios for effective and efficient communications, we need to have the antennas similarly polarized. So if we have a vertically polarized radio and we are trying to reach a repeater that has a vertically polarized antenna, we'll have maximum transfer like this. But notice if we have a vertically polarized repeater antenna and a horizontally polarized receiver, you notice the signal is much lower if you have a different polarization. So the important point is to make sure that you're aware of the polarization of your antenna and signal to ensure that we have maximum transfer. Also, we said that for HF, when a signal bounces off the ionosphere, it doesn't matter whether you are horizontally or vertically polarized at the transmitter, because by the time it bounces off the ionosphere and comes back down, the signal becomes elliptically polarized. Well, this is just a diagram to show you what elliptical polarization looks like. So if this is the standard linear polarization, they also show us what circular polarization is. But this is what the signal will tend to look like, or you can conceptualize the signal looking like this for elliptical polarization. So this here, linear polarization, and this one here would be elliptical. So if you're doing, let's say a horizontal or vertical polarization, it would be in one plane like this, but by the time your HF signal bounces off the ionosphere, it becomes elliptically polarized. So this is just to show and illustrate what elliptical polarization might look like, just for your understanding. Okay, so we will get to the question pool material in a little bit, but let's look at some things that we will be discussing when we look at the question pool. So we will come across the concept of a quarter wave ground plane, a half wave ground plane, and a 5/8 wave ground plane. We discussed that when we talked about radiation angles last class, and a little bit about a short while ago as well. So what that simply means is that the length of the antenna, in this case here for the quarter wave, is that the driven element from this point to this point is quarter wavelength of whatever frequency the antenna is cut for. For half wave ground plane, this driven element here is also a half wave in length from this point here to the base of the antenna. Those other elements that you're seeing off to the side, this is certainly not the driven element, all right? Those are called radials. So we have radials that comprise the antenna. This piece at the bottom here is simply the mast or the pole that the antenna would be mounted on. So this is the mast here. This portion here is the antenna driven element, and these are the radials. The only difference between these three antennas would be the length of them, where this one here now is 5/8 wave. So the distance or the length from this point to the tip of the antenna, that driven element or the element itself is 5/8 wavelength long. And we also have a radiation pattern diagram. So if you're looking at the antenna from the top and you're looking downwards, this pattern here, notice that the signal radiates almost equally or just about equally in all directions. This is also called an omnidirectional antenna because it's radiating equally in all directions, right? So this is the radiation pattern of these antennas. When you look at it from the top down, it's going out in all of the directions pretty much equally. And this is contrasting with beam antennas that we discussed the last time. All right, so we also talked about the half-wave dipole previously. So this is an example of what a half-wave dipole looks like. We are looking up at this antenna. So it's going up into the sky and it's also coming down to the ground this way. So this is the antenna itself. This is just the mast to hold it. And we have the feed line feeding the antenna. And notice for our half-wave dipole, this entire length of the antenna from this point to the end is half-wave. So that means from the center of the antenna to the tip would be quarter wave. So you have quarter wave here and quarter wave here, which makes up the half wave. So this is why it's known as a half wave dipole. But notice the radiation pattern also is omnidirectional if we are looking down at the antenna, right? Looking down, we notice that the signal travels in all directions equally. So this is the radiation pattern of a half-wave dipole. Notice it's similar to the quarter-wave antenna. We refer to this as omnidirectional. All right, so we're talking last class, we talked about directional antenna called the beam. So we need to be aware of three different types of antennas that are directional. We have the quad, the Yagi, and the dish. All right, so forgive me, I neglected to label these, but when you get your slides, I will try to put the labels on. This first antenna on the left-hand side, we came across this already. This is a beam antenna. We have the driven element in the center here, and we have two other elements that we refer to as parasitic elements. So we have a reflector and a director. So the driven element in the center. So this is a 3-element beam, and this will cause the antenna to be very directional. And in the case of this picture here, the antenna will radiate in this direction. All right. So this is the radiation pattern. The pattern is actually reversed to the antenna that you're actually seeing here. So think about this antenna pointing in the opposite direction, please. And if we were to look at the radiation pattern, notice that we are looking at the antenna from the top down. So we notice that some of the signal is going off to the back of the antenna here, right? In this diagram here, the back of the antenna is this area. So please think of the antenna pointing in the opposite direction. And notice that towards the front of the antenna, we have very strong signal. So towards the front of the antenna, you have maximum transmission. So this is the radiation pattern of a beam. If we were to look, or we also call this sorry about that. We call the beam antenna a Yagi. That's Y-A-G-I, a Yagi antenna. This next antenna on screen is called a quad antenna. So notice the configuration of the elements. You have the same center or driven element that you feed, and then you have a reflector element and you have a director element. And that means that the signal travels in this direction strongest. It's a very directional antenna. And if we were to look at the radiation pattern for this antenna, notice that it's very strong in the forward direction and relatively weak, even weaker than the previous diagram. Notice it's very weak to the back here and very strong to the front. Again, like the other antenna, please think of this antenna as pointing in the opposite direction. All right, so this is the radiation pattern. Notice the directivity of the antenna. This is comparing and contrasting with, let's see if we go back to it here, the omnidirectional antenna where the signal radiates in all directions just about equally. Notice with the directional antennas, you have a strong signal in a particular direction and it's weaker off the sides and to the back. And then we have the dish type antenna. You may be familiar with these antennas, DirecTV and even Wi-Fi antennas and so on about. So this is a dish antenna. Notice it is even more directional. Very, very strong, very sharp lobe towards the front. Very, very sharp, right? Much sharper than this previous diagram and certainly much sharper than the previous diagram as well. A very sharp signal concentration in one direction. Again, sorry about this, the antenna is actually pointing in the opposite direction. So think of this antenna as pointing towards the right. And if you do that, we will see what the radiation pattern is for this antenna, right? So the takeaway here is that these antennas, the Yagi, the quad, and the dish are highly directional antennas. Another antenna that we look at is called the rubber duck, or fondly known as the rubber ducky. They are found on handheld radios, or what we will sometimes call walkie-talkies. So this is an example of a walkie-talkie or handheld radio. And the antenna on that handheld radio is often fondly referred to as a rubber duck antenna. Now, the antenna itself is expanded a little bit here in the center for you to see how it looks, all right? And towards the right here, the antenna, the outside has been removed. And notice really what is inside of here is a coil of wire. Remember we talked about inductors and using a coil to shorten the physical length, total length of an antenna using a coil. So that's what they're doing here. But because the antenna has been loaded using a coil, it's not a very efficient antenna. So just bear that in mind, that these rubber duck antennas, while they work, they are relatively inefficient because they have pretty much a coil of wire inside of the antenna to shorten it for convenience. Another concept that we need to be aware of is that of shielding. So the same walkie-talkie or handheld radio, imagine for a moment that you were inside of a car and you have the antenna with the radio inside of the car. And let's say we're operating on the VHF band. What will happen is that the car's body, because it's made of metal, will shield the signal. So if you're trying to transmit sitting inside of your car, the signal, most of it will bounce around inside and not really get out. Some of it will get out, but the majority of your signal will be trapped inside of the car. And I don't think that's your intention, right? But notice if we were to put an antenna outside of the car, on top of the car, for instance, and if we had a cable going from the radio to the antenna, notice that our signal will go or get outside quite effectively. So we say if we are using a radio inside of a car like this, the shielding effect will attenuate or reduce the signal from getting outside and be very inefficient and ineffective. So bear in mind the shielding effect. So we just talked about connecting an antenna to a radio. So if I have a radio, so this is a radio transceiver. It could be mounted at your home or it could be mounted inside of a vehicle, all right? So to connect the radio to the antenna, remember it's our antenna that the signal or the radio waves will emanate from, right? So we need to connect our antenna to the radio. The cabling that's used to connect our radio to the antenna is called the feed line. One of the most popular type of feed lines that we use in amateur radio is called coax or coaxial cable. And for the technician class, we need to be aware of the type of cable that we're using and some of the properties of that cabling. So two types of cable that we use or can use for amateur radio coaxial cable is the RG58 cable and the RG8 cable. The impedance of the cable would be 50 ohms. That's the standard impedance for cables in the amateur radio space, 50 ohms. You'll come across this again, and we'll also discuss a bit about what impedance is in a little bit, all right? But for the RG58 cable, we have put on the chart what the loss per 100 foot is. So notice for RG58, the loss for every 100 foot at the VHF part of the band is 5.1 dB loss per 100 foot. But notice, if I use that same RG58 cable in the UHF band, notice my loss is higher, 9.8 dB loss per 100 foot. So what this is telling us is that the loss associated with any given cable is determined or dependent a lot by the frequency that we're using. So at the VHF part of the spectrum, or the VHF frequencies, the loss is less compared to the UHF part of the band or UHF part of the spectrum, right? So let's see what happens here. If I'm using RG58 cable on the VHF spectrum, and I'm using 100 foot of cable, I get a loss of 5.1 dB. And if I'm putting out 100 watts from my radio, so my radio is putting out 100 watts to get to the antenna. If I'm using RG58 cable, that 5.1 dB loss means that I will only see 31.3 watts at the antenna. So all of that signal, you know, approximately the majority of my signal is actually being lost in the feed line itself, right, as heat, all right? So that's not very good, but it's even worse if I'm using that same RG58 cable on the UHF band. Look at the loss, 9.8 dBs. And what that translates to, if I'm transmitting 100 watts out of my radio, only 10.5 watts get, 10.5 watts of that get to the antenna. So imagine that I'm losing 90 watts. I'm transmitting 100 watts, but because I'm using RG58 cable, which has losses of 9.8 dB per 100 foot, it translates to a major loss, almost 90 watts I'm losing using that cable. So that's being lost as heat and so on. Not very efficient, not very effective, all right? Very similar to, imagine WASA is pumping out water from the reservoirs and water treatment plants to your house. But just imagine that the mains have leaks along the road. All of that water is being wasted in the roadway that could have gone to the house. That's what's going on here. So think of this very lossy cable as wasting a lot of your power. The other type of coaxial cable that we look at is the RG8 cable. Now in another slide, I will show you the difference between the two cables. But for now, notice that the impedance is also 50 ohms, but the loss is different. Notice that the loss compared to RG58 is a lot less for both VHF and UHF. So RG58 cable has a loss of 2.3 dB per 100 foot at the VHF band. Compare that to 5.1 dB loss. It was a higher loss for the RG58. But RG8 is a less lossy cable, but notice there still is loss, 2.3 decibels of loss per 100 foot. What that translates to, when we calculate it, we get 58.3 watts output. So I'm putting in 100 watts from the radio into the feed line, and I'm only getting 58 watts. Not too bad, I suppose, but we're still losing approximately just about a half of it. So just note that feed line has losses. That's the takeaway. Once you're connecting your radio to the antenna via feed line, you have losses. And of course, you can use a higher quality cable or a lower loss cable, or you can shorten your feed line because this loss of 2.3 dB is per 100 foot. So if you were to half that to 50 foot or 50 feet or 25 feet of cable, the loss is less. So the lesson here is shorter the cable, the less loss as well. All right, let us just finish up this table before we take a quick break. Notice that for the RG8 cable, in the UHF band, the loss is 4.4 decibels, which is much higher than 2.3 decibels for VHF. So notice again, this is suggesting to us that for a given cable, the higher the frequency, the greater the loss. The lower the frequency, the less or the lower the loss. All right, let's see. Yes, good evening to you, Eric. Right. So for RG8 cable, if I'm using it on the EUHF band and I have a loss of 4.4 dB, that translates to I'm only getting an output of 35.7 watts. So imagine that, right? I'm transmitting 100 watts of output power from my radio going through the feed line, and I'm losing over 60 watts just going through the feed line, so that only 35.7 watts ends up on the antenna, and that is what's going to leave the antenna to go to the receiver who's trying to listen to me. So feed line is very important. So at this time, let us take a very short break, and we'll be back in about 2 minutes. So please take a stretch, have some water, have a bathroom break, and we'll be right back. Okay, everyone, welcome back. Okay, so we talked about coaxial cable, or coax, as we fondly refer to it. And we mentioned RG58 cable. So bottom left-hand corner, you'll see the RG58 cable. Notice it's relatively thin. And RG58 cable on the right-hand side, it's a thicker cable. So it's also less lossy. And there's a general rule of thumb that the thinner the cable, the lossier it tends to be, and the thicker the cable, less lossy. Again, rule of thumb, right? And this is how coaxial cable is constructed. You have the outer insulation, there's a braid, copper braid on the outside, sometimes called the shield. There's a dielectric on insulation, and inside of that you have the copper cabling, all right? So that's how you have the transmission line made up, or the feed line, coaxial cable. Another type of feed line is called hard line, sometimes called air insulated hard line. Sometimes hams refer to it by one of the brand names, Heliax. So if you ever heard of Heliax, Heliax is an air insulated hard line, and it's very much constructed in a rugged form. It's very hard, hence the reason hard line. It's difficult to bend. Notice the copper corrugation on the outside, and notice the solid nature of the center pin as well. And there's an insulation on the inside as well as the outside. So these are the types of, some of the types of feed line that you will encounter. Coax cable, coaxial, RG58, RG8, and air insulated hardline, also known as Heliax. So on the ends of the cable earlier, you would have seen some connectors. So there are two types of connectors we will discuss. One is called the PL259 cable. Let's see. Yes, Andrew, very good question. So there's nothing wrong with thinner cable, nothing wrong with it. There is an application. So mobile applications, for instance, you're using a mobile antenna with a mobile radio, and the length from the radio to the antenna is what, 10 feet? Certainly not 100 feet. So it's a very short run. And then remember, you're trying to get from the outside of your vehicle. So you're probably going through the trunk, or you're going through the doorway, or some firewall or something where you don't want to punch a very large hole. So you can use the thinner cable. And there are also lower loss thinner cable as well. That's why I said rule of thumb earlier. So you want to get the lowest loss cable, but you also want to have the shortest run. So for convenience, sometimes patch cords are also made up using the thinner cable. If you want to connect a radio to another device, such as a meter or a tuner, and we'll come across those devices shortly, you create what you call patch cables, and you can use those cables for very short runs. I mean, the loss per foot or per 100 foot is a lot, but if you're using a very short run or short length, then the loss might be acceptable. The thinner cable is also much more flexible. So depending on your installation, you may need very flexible cable, or sometimes you want to do a temporary installation and so on. So yes, it has its places, Andrew. Very good question. Thank you. You're welcome. So this is called the PL259 connector. It's suitable for use on the HF part of the band. It can also be used on the VHF part of the band, but it is not recommended for UHF and above. For UHF and above, the N-type connector is recommended. So on the right-hand side, you'll see the N-type connector or the N connector, versus the left-hand side, you have the PL259 connector. And notice where you might want to use it. It doesn't mean that you cannot use the PL259 on UHF, you know, it doesn't mean that. But what it means, it will not be optimal. You'll have more losses associated with it. So you should not. It doesn't mean that you cannot, but really you want to avoid it. If you can, use the N-type connector for UHF. It doesn't mean that you cannot use the N-type connector for VHF and UHF, you know, but it will be a bit of an overkill. These connectors are a bit more expensive than the PL259s. But you can certainly use the N-type connector on HF. No harm there really. It's a low loss and it will work really well. But we're talking about optimizing, and therefore the PL259 for HF and VHF and the N-type for UHF. At least that's what your exam questions will be based on. Another concept we need to be aware of, and you'll see these questions in the question pool, is standing wave ratio, or SWR, standing wave ratio. Now, we talked about a transmitter or transceiver, and then we talked about a transmission line or feed line, and then we talked about the antenna. That's the three components we've been talking about in our radio system thus far. But bear in mind that you need to match the impedance of your antenna to that of your transmission line. Your radio is expecting a 50 ohm impedance. So therefore, if your antenna is not properly tuned, and we like to say hams are matchmakers. That's what we like to do. We like to matchmake. We like to have a resonant antenna. We like to match the antenna impedance to that of the transmission line. And that's why we always talk about tuning our antenna so that the impedance at the point where the transmission line meets the antenna is at 50 ohms. And we want to have this antenna, the property of that feed line should be 50 ohm. That's why when we are using cable for amateur radio purposes, we need 50 ohm antenna, not 75 ohm, sorry, 50 ohm feed line and not 75 ohm, for instance, right? You will see for cable TV, RG59 and RG6 and so on that you use for your cable TV flow and so on that will run coaxial cable. If you look at it, you'll see RG6 or RG59. And when you look at it, you'll see 75 ohms. You should not use that for amateur radio. Not that you cannot, right? But you should not use it because you really want to match a 50 ohm antenna to a 50 ohm transmission line to a port on your radio that is expecting an impedance of 50 ohms. So that's when we say hams are matchmakers. We like to match the antenna to the transmission line, to the radio. And what happens is if it's not matched, you tend to have reflections. And that reflection will come back down and cause wastage of your transmit power. If you're reflecting your signal, why would you want to reflect it? You want all of your signal that leaves your transceiver or your radio to go through to the transmission line. You want 100% to reach the antenna and to go out as radio waves into the sky and to be able to communicate with another radio operator locally or around the world. You don't want to waste that signal. You don't want that signal to reach the antenna and reflect back down your transmission line back into your radio, right? But that's what happens if your antenna is not properly tuned and you don't have proper matching between the antenna and the transmission line. It sets up what is called standing wave. And that reflection, when you measure it, the forward power versus the reflected power, the ratio is called standing wave ratio, SWR. The ideal standing wave ratio is 1:1, right? So you're aiming for 1:1, but notice you have 1.5 to 1, 2 to 1, 3 to 1, 4 to 1, 5 to 1, and so on. High standing wave ratios are bad. You don't want to, when you measure your SWR on your antenna, you get a 3 to 1 and a 4 to 1 and a 5 to 1. You're wasting a lot of your signal. What you want is certainly less than 2 to 1. So all 1.5 to 1 and so on, excellent. 1:1 is ideal if you could achieve it, but certainly less than 2 to 1. Some people operate their transmitters on HF for 3 to 1 and so on, but you're losing a lot of power and you're heating up your equipment unnecessarily. And depending on how high it is, you might even end up damaging your equipment. So you want a low SWR. So when you have a low SWR, perfectly 1:1 is ideal. It's a good match. It means that your radio or your transceiver is transmitting the maximum power through the transmission line and getting to your antenna, and all of that is going out. If you have a 1:1 match, remember, hams are matchmakers. But if you don't, the rest of that is lost in heat. So notice that you want to get an SWR of close as possible, 1:1. All right, so we have a meter called the SWR meter. And where do we install that meter if we have one, right? So this diagram shows us here that we have our radio transceiver, and we have our antennas before, and we have our feed line. So the best place to put the SWR meter is right after the radio, so that you have a jumper, or a pigtail as it's sometimes called. You'll connect your radio to the SWR meter, one port, and the other port of the SWR meter goes to your feed line that goes to your antenna. So this is where you will physically connect your SWR meter and read off your SWR. Again, remember, hams are matchmakers. Now, there are different types of meters that will help you measure your SWR. One is the pure SWR meter, right? It will just read it off for you here. The other one is the directional watt meter. Remember, we said that SWR is a ratio between the forward and reflected power, right? So it's a directional watt meter. You turn it in this direction, you get the forward power. You turn the switch into the opposite direction, you get the reflected power, and you can determine the ratio. You can also use an antenna analyzer connected to your antenna, and it will tell you what your SWR is and so many other things as well about your antenna. So just note these three devices: SWR meter, directional watt meter, antenna analyzer, and this is sort of what each one looks like. Another device that you need to be aware of is called the antenna tuner. Remember we said hams are matchmakers? Well, what happens if your antenna does not match? It's a little bit long, it's a little bit short. Do you go and cut the antenna? Do you go and add a piece to lengthen it? And then remember, you're using that antenna on various bands. So hams often use an antenna tuner. For example, what's shown here on the left-hand side. We will connect our radio to the antenna tuner and then the antenna tuner to the antenna. We will manipulate the dials and we will tune that antenna. So it's called an antenna tuner. Also, sometimes as hams, we want to test our radio, but we don't want to transmit and have our signals going off into space where people will hear us testing 1, 2, 3, testing 1, 2, 3, 9 Zulu 4 Omega of testing. We may not want someone to hear that. We may just want to see if our radio is putting out the required power, what our audio level might be. So I may not want to transmit the signal using an antenna. I can use something called a dummy load, which is essentially a resistor at 50 ohms. I can connect this to my radio and transmit into the dummy load, and my signal will really not get very far. Certainly not as far as if I were to put it into an antenna. So be aware of this device called a dummy load. All right, so let's go straight into the no-nonsense guide. And pick up where we left off. Right. So, last class, we reached page 34. And let's look at page 35. We dealt with what a rubber duck antenna was in the slide deck, right? So they make note here and tell us that it uses inductive loading to make them shorter than a full-size antenna. That means we're using a coil. However, they also tell us that when you load them like this, it makes them less efficient than a full-size antenna. So that's the rubber duck antenna. So let's go straight into the question, pool question on rubber duck antennas. What is a disadvantage of the rubber duck antenna supplied with most handheld radio transceivers when compared to a full-size quarter wave antenna? Well, we know that it's not a very efficient antenna. So the answer is it does not transmit or receive as effectively. All right, so remember we said that the rubber duck antenna is not a particularly good antenna. It works, but it's not particularly good. All right, so next question in question pool. What is a disadvantage of using a handheld VHF transceiver with its integral antenna inside a vehicle? So the integral antenna that they're talking about for the handheld is the rubber duck antenna. You see how they try to ask you things in a very sophisticated way? They try to tie you up. But when they say integral antenna, they're talking about the built-in antenna on the radio. And the built-in antenna on a handheld radio is also called a rubber duck antenna. So what is the disadvantage of using it inside a vehicle? Remember that picture we showed, very lovely car and the handheld radio inside, and we said shielding prevents the signal from getting out. So let's see what the answer is. Signals might not propagate well due to the shielding effect of the vehicle. All right, so just remember that little diagram where we showed the car and the handheld radio inside, and we saw that the signal bounced around inside, and most of it stayed inside and just a little bit might have gotten out, right? So that's the shielding effect when you use a handheld radio inside of your vehicle. Right? And they tell us that the metal frame will prevent some of your signal from getting outside. And they also talk about getting to repeaters. As a matter of fact, we have some radio operators that will use their handheld radio inside of the car and will wonder, wait a minute, why am I not being heard too clearly? So some of you are probably just turning on a light bulb in your head. So, oh, that's why when I use it from inside the car, people telling me I'm not being heard properly. But if I step outside of the car, they hear me clearly. It's because of the shielding effect of the metal frame of the vehicle. So they tell us here a better option is to use an externally mounted antenna. So remember the picture with the car, we showed an antenna on top of the roof, right? So you can use an externally mounted antenna, 5/8 wave better, all right? So let's look at the question in the question pool. What is an advantage of using a properly mounted 5/8 wavelength antenna for UHF or VHF mobile service? So that question has to do with the radiation angle diagram that we looked at, where we saw quarter wave, half wave, and 5/8 wave, all right? So the answer is, or the reason why the 5/8 wavelength antenna has an advantage for VHF and UHF is because it has a lower radiation angle, meaning it goes further, the signal goes further, and it has more gain than a quarter wavelength antenna. So just think about that diagram where we saw the signal going further using 5/8 wavelength antenna versus the half wave and the quarter wave. So we dealt with feed lines, and we said that we use feed lines to connect radios to antennas, and there are many different types. So the ones that they talk about here is there's coax cable or coaxial cable, there's ladder line, twin lead, open wire feed line, and so on. And probably for our next class, we can show you what these other types look like. But they say that coaxial cable is the most common type. Question in the question pool. Why is coaxial cable the most common feed line selected for amateur radio antenna systems? The answer to the question is that coaxial cable is easier to install, or it is easy to use, and it requires few special installation consideration. All of that is to say, it's easy to use. Right. So they tell us here that when we are choosing the feed line, an important consideration is to match the impedance of the feed line to the output impedance of the transmitter and the input impedance of the antenna. So remember we said that hams like to matchmake. We are good matchmakers as amateur radio operators, right? So we are matching the impedance of those three things, right? Now we need to discuss what impedance is. If you recall, when we were looking at DC circuits, we talked about resistance. So you could think of impedance as resistance, except that impedance applies to AC circuits. So that's what impedance is. Impedance is the opposition to flow of current, but AC current, whereas resistance is the opposition of flow. You could say for DC current, all right? Let's just say that for the time being. But impedance really comprises of resistance plus something else called reactance. And for reactance, there are two types. There's capacitive and inductive reactance. So for our purpose, we need to know that impedance is the opposition of flow to current in an AC circuit. So let's go straight to the question in the question pool. Simply, what is impedance? Well, we just said it. Impedance is the opposition to alternating current flow in a circuit. So think of impedance as resistance or a type of resistance. That's the best way to think of it. Just like resistance resists the flow of current, impedance impedes the flow of current. And because we said that you can think of impedance like resistance, here's this other question. What is the unit of impedance? Well, what was the unit of resistance? If you recall, the unit of resistance was the ohm, and therefore the unit of impedance, likewise, is also the ohm. So we're in solid ground when we say, think of impedance like resistance, all right? Remember, we also said that amateur radio transmitters love 50 ohms. So you'll be talking about 50 ohms in amateur radio, not 75 ohms, 50 ohms. They also tell us that most antennas have an input impedance close to 50 ohms. Right? Question in the question pool. What is the impedance of most coaxial cable used in amateur radio installations? So remember that figure, 50 ohms, 50. And they also tell us here that RG58 and RG8 coaxial cables, those are the cables we looked at in the slide deck. They are often used in amateur radio stations, and the impedance, both of them, would be 50 ohms. Now they tell us that coaxial cable has some disadvantages. Remember we looked at the loss chart for both RG58 and RG8. They are noting here for us that coaxial cable may be lossy at high frequencies. Remember we saw for UHF how lossy it was, especially for the RG58 cable. All right. Question in question pool. In general, what happens as the frequency of a signal passing through coaxial cable is increased? All right, so let's strip this question down a little bit. They're asking us, what happens when the frequency is increased? Right? So remember, frequency increase. That's what they're asking us about. And they're talking about when the signal passes through what? Coaxial cable. Notice when the table that we looked at, when we increase the frequency, we had a higher loss. So that's the answer. When you increase the frequency of a signal in coaxial cable, the loss increases. Next question, what is the electrical difference between RG58 and RG8 coaxial cable? This is straight from the chart that we looked at. The loss for RG8 cable is less for a given frequency. All right, when you compare it to RG58, remember the RG58 cable, the loss was higher, both at VHF and UHF compared to RG8. So that's what they're asking us here. The loss for RG8 is lower. And we made this point earlier, the smaller the diameter of the coaxial cable, the higher the losses. Notice this is in general. All right, so always take a grain of salt with some of these generalized statements, right? Because you may see some very thin cable that are low loss as well. But in general, smaller the diameter of the coaxial cable, the higher the losses will be, right? You could kind of think of it as the smaller the cable, the more resistance will be encountered to the signal traversing. If that helps you conceptualize that, you know, think of it that way. And also, we talked about this as well, that the longer the feed line, the higher the losses. So remember when Andrew asked that question, you know, why should we use the thinner cable, or what is it good for? Well, if I use a short piece, that's okay. But if I use a long piece, I will have very high losses, right? Okay. Which of the following types of feed line has the lowest loss at VHF and UHF? Remember, we looked at 3 types of cable in the slide deck. We looked at RG58 and RG8 coaxial cable, but we also looked at something called hardline or air insulated hardline, and we said that was extremely low loss cable. So that's the answer that they're looking for. Air insulated hardline. All right, so they tell us that another disadvantage of using coaxial cable is that it is more sensitive to moisture, right? Meaning water, right? So if that coaxial cable gets wet or water gets inside of that cable, problems. So bear that in mind as an amateur radio operator. When you're installing coaxial cable, be sure to seal it properly. Question in the question pool. Which of the following is the most common cause for failure of coaxial cables? Well, we just said it. Moisture contamination. That's when water gets inside of the coaxial cable, troubling the place. So always seal up your coaxial cable when you make them up, especially the part that goes on the outside by the antenna and it's facing the elements. Sometimes moisture enters cracks in the cable. Remember, we have an outer jacket, the insulation on the outside. Sometimes the ultraviolet light will cause that to become brittle and crack up, and water will get inside there. That's the basis of the next question. Why should the outer jacket of coaxial cable be resistant to ultraviolet light? So the simple answer is that UV or ultraviolet light can damage the outer insulation or the jacket and allow water to enter the cable. And we said water entering that cable, very bad. It will cause the impedance to change. It will cause the loss to increase. So very, very bad. They also tell us that even though an insulated hardline is excellent cable, it's also susceptible to moisture. So you need to make sure those cables are also properly sealed. Question in the question pool. What is the disadvantage of air core coaxial cable when compared to foam or solid dielectric types? All right, so what we're talking, let's dissect this question. Disadvantage of air core coaxial cable compared to foam or solid dielectric types. That means instead of using air, you have something else as the filler or as the dielectric, such as foam or something else that is solid, like some sort of polyplastic. All right. If you're using air core cable, you need to make sure it is properly sealed. So it requires special techniques to prevent water absorption. Remember, water is the enemy to your coaxial cables. Which of the following is true of PL259 type coax connectors? Remember, we looked at the PL259 connectors and the N-type connectors, so that's what they're asking us about. Which of the following is true of PL259 type coax connectors? Remember, we said that we can use that for HF and even VHF. So that's the question, that's the answer here. They're commonly used at HF frequencies. Remember, HF is 3 to 30 megahertz. Well, PL259 connectors are very popular for that part of the band. They also tell us that PL259 connectors are not the most suitable when operating at higher frequencies. However, type N connectors are much better, right? So we did discuss that. Question in the question pool. Which of the following connectors is most suitable for frequencies above 400 megahertz? Now, where is 400 megahertz? Remember, we said that UHF is 300 to 3000 megahertz. So that means 400 megahertz is in the UHF band. So they're asking us a question about the UHF band. And when we looked at our diagram with the two types of connectors, PL259 and N-type, which one did we say will be suitable for the UHF band? We did say the N-type connector is suitable for UHF. Also note that the PL259 connectors are not waterproof. So therefore, if we are installing them outdoors, like let's say you have an antenna on the outdoors and the coaxial cable is going up to it, you have a connector that's a PL259, you have to make sure that it is sealed in some way, otherwise water will get in. And when water gets in, what happens? You have increased losses and you will eventually have failure of that cable. All right, so we're going just a little slightly over time. We started a few minutes late due to some technical difficulties with the link. So let's just press on a little bit further. Next question. Why should coax connectors exposed to the weather be sealed against water intrusion? Well, that's asking the question that we just discussed here. The reason is we don't want water to get inside of there because we want to prevent an increase in feed line loss. Remember, if water gets in there, you'll have more losses in the feed line. So we seal it to make sure that we do not have any additional feed line loss. Okay, so they say coaxial cable connectors can be a real pain to install properly. Well, maybe the first time it could be a little bit of a challenge, but it's certainly doable, all right? But if you don't install it properly, right, because you need to solder, some of them are crimp type, you need to make sure they make a solid connection. If not, you will have a loose connection, and that could manifest itself in greater losses, intermittent connectivity. And if you have an SWR meter, you will see the SWR fluctuating quite a bit. All right, so just bear that in mind, that when coax cable connectors are installed, that you do so properly. PL259s might be a little bit easier to install compared to the N-type connector. So that's why they're talking about could be a real pain. Yeah, N-type connectors could be a little bit challenging, but certainly doable. Question in the question pool. What can cause erratic changes in SWR readings? The answer is a loose connection in an antenna or feed line. So if your coax connector like the PL259 or the N-type connector is loose, you can see fluctuations in your SWR. So that's one of the ways that you can tell you have a poor connection. Yes, so you can, so Anthony, thanks for the question. You can use good quality coaxial cable that is UV rated, intended for use in ultraviolet environments. Sometimes you may have a marine environment as well, so you need to use cable that is suitably manufactured for UV. Also, at the ends where you have the coax cable and the connector, you may want to apply sealant that will also protect the ends from fraying out as well, right? Appropriate coax seal will work just fine at the ends. But like everything else, just like electrical cable in your house, you should check the insulation and change it out from time to time. All right, so no cable lasts forever. But once you select the right type of UV related cable, you will get the maximum life out of it, but you will eventually need to change that cable as it deteriorates in the sun. Good question there, Anthony. All right, so we have made some pretty good progress. Let us see if we could spend a few more minutes and deal with some of these questions here to end off this section. All right, so we're taking a few minutes into overtime, considering we started a little bit late. So please bear with us. So we talked about SWR, or standing wave ratio. Hams talk about SWR all of the time. You want to have a low SWR. Remember, we say hams are good matchmakers. Well, SWR is a measure of how well matched the feed line is to an antenna. We discussed that, right? Question in the question pool. What in general terms is standing wave ratio? We just said it. It's a measure of how well a load is matched to a transmission line. And they say here to us that a load for intents and purposes is the antenna. They also tell us that the higher the SWR, the greater the mismatch, meaning your signal will be, a lot of your signal will be lost as opposed to getting out of the antenna and going to where you want it to go to your receiver. What reading on an SWR meter indicates a perfect impedance match between the antenna and the feed line? Remember that little graph we looked at and we talked about the SWR could be 1-to-1 all the way up? Well, that's the antenna. The perfect or the ideal SWR, difficult to achieve in practice, maybe for one spot frequency, but certainly otherwise, yes. Okay, Lisa, noted. We will finish off this section very quickly. Yeah. What does an SWR reading of 4:1 indicate? Well, just like we have 1:1 as being a very good SWR, 4:1 is a very bad SWR, which means that we have mismatch, impedance mismatch. All right. Another question, similar related. Why is it important to have low SWR when using coax feed line? Again, we want to reduce signal loss. So that's why we try to have our systems properly matched so that we have the least amount of losses. What happens when the power is lost in a feed line? Remember we said that it gets converted into heat, so that's the answer. The reflected power gets converted into heat. That's very wasteful for us. Why would you want your signal from your radio turning into heat? You want that signal going out of the antenna to reach your destination. We had a diagram that showed this, so we'll deal with this question very quickly. What is the proper location for an external SWR meter? Remember the diagram, we showed the radio, and right after the radio was the SWR meter, then the feed line going to the antenna. So we install the SWR meter between the transmitter and the antenna. So you can just look over that, that diagram. All right. So let's stop here on page 39. All right. So again, I do apologize for starting a few minutes late. The link that was sent to you had an error for some reason. So I'm glad everyone is able to get on eventually. Thank you so much. Our next class will be scheduled for Friday, the 24th of July. And please feel free to ask any questions via email at the beginning of the class. We will try to deal with those questions. So I'd like to thank you for your time and your attention. Trust that everyone is going well with the class. Feel free to look at the practice exams. You can take those now to see how you're doing. Again, thanks a lot for the questions. Yes, Charlene, really appreciate that. Also, do have a good weekend, restful, and be safe, everyone. Have a good night. Thanks so much.